500-gram disc, the radius is 25 centimeters, on a 2-meter-long ramp inclined 25 degrees with the horizontal, experiencing a coefficient of static friction of 0.4. I'd like to know how fast it's going at the bottom. And I'd like to know what the size of the frictional force is on it. Let's start with the method we had in class for finding the velocity. That was a conservation of energy method. Now, you didn't have to do that. You could start this problem from force and get the acceleration and use a motion equation to get the velocity. You're going to have to get the acceleration anyways if you want to get the frictional force. So there's no reason you had to do energy first and then the force part. You could have done the whole problem with forces. But since many of you did the energy problem, let's do the energy problem. So I'm going to slide it over there for a minute and start off with the idea that the object starts with gravitational potential energy. And when it makes it to the bottom, it has two forms of kinetic energy. Does that work out okay for everybody? That's what the vast majority of you did. That's not a problem if you know how to get each of these pieces together. I didn't provide very much. For example, I didn't give you the height. I told you it went 2 meters down the ramp. You needed to figure out the height. It's a triangle problem, of which the height is related to the hypotenuse. I gave you the hypotenuse. So if you want the height, you had to do 2 times the sine of 25 degrees. So some of you need to correct your work for that. So mg 2 sine 25 for the height. 1/2 mv squared, not a whole lot to do there. However, moment of inertia, it's a disk, and I say it's a disk. So you're going to need to use the moment of inertia of a disk. So 1/2 mr squared. And then you're going to have to drop in a conversion from the angular velocity to the linear velocity. That's going to be v over r squared. All right. Any questions about those? So then I'm not sure what happened next, but a few of you really screwed up from here somehow. The right side ends up being 3/4 mv squared. The left side, still mg 2 sine 25. Cancel out the m's, solve for v, and you get the square root of 4/3 times g times 2 sine 25. And that ends up being 3.35. We good? There are a few missteps in there, little stuff. But again, in trying to make sure we are as accurate as possible and doing all the steps possible, I don't think you can get the velocity without doing every one of the steps that's here if you're going to use energy. Just don't think there's any other way to it. So some of you, it was as simple as not doing the height correctly. Some of you, it was a little bit more complex. One thing to keep in mind, it's never going to be faster than the square root of 2gh. It won't be faster than that. So you can always get the square root of 2gh real quick and make sure that your number is not bigger than that. It'll have to be smaller. So the next part, I think there's more difficulty. So let's take a look at the next part. I asked for the size of the frictional force. I'm saying that because I got a variety of other answers as I walked by. I had people tell me the acceleration. That's fine. You have to use that to get the frictional force, no doubt. I had people telling me what the coefficient of friction was. Well, I gave that to you. So there's nothing to solve for there. More importantly, did you actually need the coefficient of static friction? only in that you had to stay below a certain amount of friction. If your frictional force was greater than that, did you test your answer against the maximum available amount of friction? You could have, because we know the maximum available amount of friction comes from this, which it's on a ramp. So there's really no secret about it. Box on a ramp. Frictional force is going to be based on mg cosine theta. Now, I'm going to just set that aside and consider that we had to do a force problem. And we had a choice in doing our force problem on where to set our pivot. We could set our pivot in the middle of the disk, or we could set our pivot at the edge of the disk. There is a more beneficial answer here that makes this faster. But across the course of Friday, I worked the problem both ways, so that anybody who wanted to look up the answers or look at the work could have gone on YouTube and seen both derivations. Which one do you want me to use here? About the center or about the edge? Okay. That's the longer of the two ways, just so you know. So which one did we do on Friday? Then I'm doing the center. I'll show you why. But if we did the edge, then you have everything you needed to get the answer. I think I just left it in terms of I. So you just plug in 1/2 mr squared to get the acceleration. I'm going to purposely do it different in this class, so you see both derivations. But I am going to skip some steps. So if you were out and you don't understand why I'm choosing a step, you should ask. Or if you were here and don't understand, you should ask. Ready? There is nothing different about the net force in the x direction problem. It is still going to be mg sine theta minus friction equals ma. I see no reason to do any more work than that. Now, you have a picture already that shows the forces acting on the disk at the point where they act. And we'll probably understand this part better if you look at that picture. But I'm going to, just to make sure we're all in on this, remind you that there is friction that acts this way. There's normal force that acts that way. And there's weight, which acts that way. All good? Any question? If I choose the center of the disk to be my pivot point, then the friction is applying a torque with a torque arm length of the radius of the disk. And that torque is in this direction, which is the positive direction of turn, because it's going down the ramp. Any question about any of those things I just said before I zoom back out? Please, if you don't understand why I'm making these choices, don't wait and don't act ignorant now when you could use this information later. Yes, sir?
So the normal force doesn't cause torque because the angle is 0, right?
In the case of this one, because I've chosen the pivot point to be at the middle, the normal force does not cause a torque because the angle would be 0 degrees. Okay. That is correct. The normal force points directly towards the center. So if my torque arm were along this length, the normal force is pointing straight back, and that would be an angle of 0 degrees in my torque equation. I'm not reiterating it necessarily for your benefit. I'm reiterating it for the class's benefit. Also, the weight doesn't cause a torque about the middle, because the torque arm length for the weight would be 0. So that's why there's only one torque that acts on the disk at the edge, and that's friction. So am I good to move on a bit? And if it's not clear why I'm choosing to do it this way, it will be right now. Let me move that over there so I have some room to work. Net torque equals I alpha. If I use the center of the disk as my point of reference, then the only thing that causes a torque is that frictional force. And my moment of inertia would be about the center of a disk. And my acceleration I can replace with the linear acceleration. I've done three things. I've written out the torque, RF sine theta. I've substituted in the moment of inertia, and I substituted in A over R. Now, if you still don't know why I'm choosing to do it this way, then watch this next step. All the R's cancel. Because I have an R down here with one of those, and I have an R on both sides. So all the R's cancel. I'm left with friction equals 1/2 ma. By doing it this way, I get an equation that is solved for friction already. If I had done this the other way, this would have produced mg sine theta equals an acceleration, which is fine, but it would make it harder to solve for the frictional force. By doing it this way, I make it easier to solve for the frictional force. But raise your hand if you would like me to be doing this in parallel with the other pivot point, because I can. Okay, I see no hands raised. I see one hand. Okay, it's not hard. If I choose the pivot point to be the edge, if I choose the pivot point to be the edge, that means the pivot point is here. Then the normal force nor friction are causing a torque. The only torque is from mg sine theta, because it's acting in such a way as to cause it to torque about the pivot that's here. Are we okay? If I do that, I'm going to run out of space, so I'm just going to take my picture away. You guys have a copy of the picture, right? I don't need a copy of the picture. So my parallel torque argument. I can't use I because I shifted the axis of rotation to the edge. So I have to use I center of mass plus mr squared times alpha. I have to use the parallel axis theorem to shift the moment of inertia to the edge. My torque now is going to be R times mg sine theta remember, it's R times F times the sine of the angle. Just putting it all in there. That has to equal center mass 1/2 mr squared plus mr squared. Out of room. So I have to squeeze this in. Times A over R. Okay. I think I've done it. Now, this doesn't give me something that I can use to find F, but it does give me something I could use to find the acceleration. First, all of the R's cancel again. Inside this parenthesis, I get 1/2 plus 1, or 3/2 mr squared times A over R equals R mg sine 25. So I'm noticing that M cancels, R's all cancel, and I get that G sine 25 equals 3/2 A. All good? Now, where can I put this? I'll put this right here. If you substitute this here, you get mg sine theta minus 1/2 ma equals ma. Add that term to the other side, cancel out the m's, and I get g sine theta equals 3/2 a. Understand, it's got to work this way. It's got to come up with the same answer. You can't get different answers if you do different methods. So it had to give us the same expression for the acceleration, whether I use the axis at the center or the axis at the edge. Are we all seeing that now? The only difference is if I do the axis at the edge, I can get the acceleration directly with no substitution. And if I do the axis at the middle, I get an expression for the frictional force. It's the only difference. But you plug that in to get your acceleration, and I think it comes out to be like 2.8 meters per second squared. Now, if you plug in you plug in 10 for g and sine 25. And so if you want the frictional force, which is right there, I just have to plug in a there. So friction equals 1/2 times 0.5 times 2.8, and I got 0.7 newtons of friction. That's what I got. 0.704 actually, but I used 10 for G. Now, there's a lot I can do here. But did we follow all of these things all the way to the end? Keep in mind, we have an acceleration. We could say initial velocity is 0. Displacement was 2 meters. We can find the final velocity. There is an equation that will do it. I'm thinking v squared minus v naught squared equals 2a delta x. Probably get us there. I'm not sure if that's more work or less work, just different work. At the same time, I don't know if you guys know this, we had the final velocity and the displacement. We could have used it to solve for this without doing the force stuff. Right? Could use the motion equation the other direction. And said that, well, we knew this was 3.35. Let's figure out the acceleration. I'm not sure that saves us as much time getting to friction. We still had to analyze the friction portion of the problem. But there are alternatives. Did anybody do this? Anybody plug it in? What do you get? So we are well under it. And 0.4 isn't particularly sticky, but we are well under it. Agreed? So we're good. All right. That's a whole lot of stuff there. But let me just sum real quick. You understand, you've done it now a couple times. They can't really do anything besides this if they're going to ask for friction. Different shape? Sure. Have it rolling up the ramp and not down the ramp? Sure. All of these things are true. And trust me, in each of these things, there's stuff to do. And this frictional force would be different if the shape were different. The harder it is to turn, the more friction it will take to turn it. I'm saying that, but listen closely, guys. Sometimes there's going to be questions on the multiple choice, and you're going to say, why did you choose that, Mr. Sheldon? I'm going to say, because I just thought it was the right answer. And then we'll work it out. It takes us 4 or 5 minutes to work out. Do you remember our last multiple choice where this was a real thing? I'm telling you something to consider. Consider committing to memory that the higher the inertia is, the more friction it's going to take to turn it. I want to work it out. A ring of the same mass will have more friction required than a disc. It's harder to turn. It's going to take more force to do so. And the object will be the same mass. There's still going to be the same limit to how much friction is available. So it is possible you could have two shapes on the same surface and one will roll and the other will slide. Because the one that is too difficult to turn may not have enough friction to do so. All right. I really don't want to do every permutation of possible ball rolling down a ramp problem that there is. You can understand why, right? They're not going to be any more or less interesting than this. On the other hand, a roller coaster question, yeah, we should do one. We should. That's why I put it in your homework. There's a roller coaster question in your homework. And let's take a